Good morning and welcome. I'm Fabio and I'm here to introduce the Copernicus Marine Bio-Asia training. In this notebook, we will see how to visualize maps, sections, and time evolution of nutrients, chlorophyll, and CO2 in the Arabic Sea. As you can see from the table of contents, we will have a short introduction, then we will get deeper into the analysis of data required to perform the 3 exercises and how to download it. Then we will see how to plot maps with the first exercise, how to plot the transects thanks to the second exercise, while in the third exercise we will see the temporal evolution. The objective of this exercise is to use the Copernicus Marine biogeochemical products to visualize some typical biogeochemical features in the Arabian Sea and in the Northwest Pacific. Section 2 is to present the data required for this notebook. In particular, as you can see from section 2.1 model description, this example is based on the product Global Analysis Forecast Bio 001-028. To get more info on the product, you can see the dedicated product page on Copernicus Marine web portal. You can download the product user manual or you can download the quality information document. Section 2.2 shows the parameters used to download the data for exercise 1 and 2. You can see the name of the product that we mentioned a little ago. You can see the name of the dataset, that is the monthly one. And you can see the bounding box of our area, that is 10-25 degrees north for latitude, 50-75 degrees east for longitude. Here you can see the time steps for this dataset and the 4 variables of interest: CHL, NO3, PO4, O2. The size of the dataset of the netcdf file used for input is around 30 megabytes, while for the third exercise we will have a smaller size of 1 megabyte. And the bounding box is comprised between 25 and 40 degrees north and 130-180 degrees north of longitude. The only variable of interest for this third exercise is CHL. Then, now that we know the parameters used to download data, we can see how to effectively download the data. We can, for example, exploit Motu Client. There is a multi-platform Python script to automate the extraction of the information from the Marine Copernicus portal. If you need to install Motu Client, you can copy this command, pip install Motu Client, paste it into a code cell, copy and paste. And you can execute this command by clicking on the play button or by hitting Ctrl Enter. Then, in this case, the requirement is already satisfied since we have already installed Motu Client, and we can go on with the execution of the notebook. Here you can see 2 commands exploiting Motu Client. And these are to download the dataset for the first exercise and the dataset for the second one. In our case, data is already downloaded in the data folder, but if you need to download this data again, you can once again copy this command into this gray cell that is used for the code to be executed. And then configure your username, your password, and type once again Ctrl Enter or click on the play button. Then we can exploit these few lines of Python code to check if the files have been created. Now that this cell is selected, I can click on on play, and you can see that the files exist, so we are ready to go on. We are ready to go on with the execution of the first exercise that is related to the plot of maps. Section 3.1 lists the modules required for the execution of this exercise, that are OS, datetime, NumPy, Xarray, Matplotlib, and basemap. The required version for this exercise of the Python interpreter is the 3.7.3, and you can check the Python version by clicking on this cell of code and hitting Ctrl-Enter. You can see that the version is Python 3.7.3, so it's compliant with the one listed above, and we can go on. If the version is different from this one, we can install the right version by copying this command, pasting it into a cell of code, and then hitting Ctrl-Enter. In our case, we don't need to do it, so I can erase the text and go on. Then we can install the requirements for the exercise, so the libraries NumPy, Xarray, Matplotlib, and so on that we listed a few lines before. And even in this case, I already installed these libraries, so I don't need to copy this string into this cell, and I can go on with section 3.2. Since the modules are already installed on our environment, we can proceed to import them by hitting Ctrl-Enter and Ctrl-Enter once again. You can see here on the left a number. This number tells that the execution of this block of code is completed. If instead of a number we have an asterisk, it means that the execution of this block of code is still ongoing. The following block of code is used to set some variables, in this case region code and notebook code, NB code. Please don't change the following constants. We just execute this block of code. You can see that the execution is complete, and we can go on. The following blocks are used to define two functions, checkdir and getRangeIndexes, and we can hit Ctrl-Enter on both of them. And I repeat once again, these two blocks only define the functions but not execute them. Then we can define the path used to access the input netcdf file and to write the output files. So data path and out path are two paths that, hitting Ctrl-Enter, are now set to data and out plus region code plus notebook code. Using the function checkdir that we defined a few lines above, we can create data path and out path if they don't exist. We execute also this one, and now we can check that the files exist on our environment. You can see that in the current directory we have these files, so we have the data directory and the out directory, and in the data path directory we can see that we have the two netcdf files that we need to execute the exercises. So we can start with the real core of the exercise, of the first exercise, and load the netcdf file by hitting Ctrl-Enter on this cell. Okay, we go on and we can, for example, read some information about the dataset with ds.info. I can execute also this block of code to read which variables are defined in our dataset, and we can see NO3, O2, PO4 and CHL that are the ones defined in the MotoClient string listed before. And we can now check the coordinates defined in the dataset with Ctrl-Enter once again. The presence of the variable depth informs us that we are using a three-dimensional dataset. We have in fact depth levels that we can read using ds.depths. With section 3.4, we can set the configuration to access the dataset, for example, the name of the coordinates, longitude, latitude, time and depth, Ctrl Enter. And we can set the variable names, so CHL, NO3, PO4 and O2. It's time now to configure the plot. So for example, we can set the bounding box to the full area described in our InputNet CDF file. And to configure the plot. So first of all, we select the month that we intend to plot, where 0 stands for February. We can configure the map and the axis. We have the configuration for the color bar, for the title and for the labels. And then we can go on to select, to draw other aspects of our plots, for example, the meridians and the parallels. We can choose to draw the countries, or we can comment these lines if we are not interested in this function. And I can type Ctrl Enter to complete the configuration of the plot and to plot the total chlorophyll. This configuration is for the month of February, as we already said, and it's for the surface value of the chlorophyll. In section 3.6, we can do this also for a summer month in the Arabian Sea. So for sure we have to change the value of J from 0, that is February, to 6, that is August. In our case, once again, we have the configuration of the plot, and hitting Ctrl Enter, we have the plot of the total chlorophyll on the surface for the month of August. We can see that the values are slightly different, and here you can read the description of why we can notice this difference between a summer map of chlorophyll and the winter one. And this is due to the southwest monsoon that we have during summer, and to the northeast monsoon that we have during the month between November and the mid of February. Section 3.7 is used to generate the map of nitrates in summer. Once again, we have to configure the variables for the plot. In this case, we are selecting the variable NO3, and we are, even in this case, selecting the full area as our bounding box. Ctrl Enter, and we have to confirm that the execution of the code is completed. And we can proceed to plot the variable. So here, as you can see from the label, from the title, we have the nitrate for the month of August at the surface. Now, if you want, you can try to change the plot. For example, you can change the variable to plot, you can change the area, or you can change the min and max values for the choose variable. Furthermore, you can also change the depth level, but only for a three-dimensional dataset. In our case, we are using a three-dimensional dataset, and we can move from the surface that we have used in our example to the other depth levels. Section 4 is dedicated to the second exercise that we use to plot transects. In this case, we start by extracting data for a given latitude value. So you can see that we select a minimum and a maximum depth level, a minimum and a maximum value for the longitude, while we have only one level of latitude, that is 20. Now we set the indexes of coordinates, and we extract the coordinate subset as well as the variable to plot. In this case, we are extracting all the four variables: CHL, pH0, NO3 and O2. If we want to check the values contained in one of these variables, we can simply type the name of the variable in this block of code, for example O2, and type once again Ctrl-Enter. Now you can see an error because I forgot to execute this code, as you can see from the missing number between the square brackets. So I execute this block of code, and once again I type O2 and Ctrl-Enter. Now you can see that we don't have the error because we correctly executed the above block of code, and we can go on with the execution of the exercise. In section 4.2, as we did for the first exercise, we can configure the plot. To configure the plot, we can set the labels for the X and Y axis. We can configure the color bar and the title and label of font as we did before. Now we define a function, plot transect, to plot the transect. And once again, notice that we are just defining a function, but we are not executing it. So Ctrl-Enter, and you don't see any results because we have just defined the function, but we still need to execute it. We execute it in section 4.3, plot a transect of nitrate. Here we can see that we select the month of August, we extract data for that month for the variable N03, and then we invoke the function plot transect. Here you can see the results. What does the nitrate section show? This nitrate section shows the inclination of the nitrocline from east to west. This highlights the upwelling of nitrate along the coast of Somalia and Oman in summer, so July and August. If you change the month, you will see that the nitrocline depends in the west of the basin. If you switch to the phosphate variable, you will see the same behavior as with nitrate. The phosphate is another macronutrient limiting the primary production. Now we can try to plot the transect of oxygen. So once again we are selecting a summer month, where 6 once again stands for August. We select that month from the variable O2, and we plot data invoking the plot transect function. So even in this case you can notice the results in this picture. Section 5 is dedicated to the last exercise proposed in this notebook. So this is an exercise to plot the temporal evolution in the Northwest Pacific Basin, and in particular in the area of the Kuroshio Current. To access the data, we now open a different file, so the one ending with X3. That is still, of course, a netsdf file, and we use again Xarray open dataset to open this netsdf file. Ctrl-Enter, and we can see that the opening of the file completes successfully. And then we can still have information of this file using ds.info. Ctrl-Enter. We can see the variables defined in these files, even if we can already read it from the previous output. Ctrl-Enter. And we can see the coordinates defined here using ds coords. In section 5.2, we can see we can set the configuration while using these variables to define the name of the longitude variable, latitude, time, and depth. And we can do the same for the variable chlorophyll. The configuration set in section 5.2 is used to set the coordinates and the variable's name. So Ctrl-Enter on the first block and Ctrl-Enter on the second block. In section 5.3, we can finally focus on the generation of the temporal evolution plot for the chlorophyll, what is called Hofmöller diagram, lat time. Here, once again, we choose the variable to plot. We set up the arrays of coordinates for the selected dataset, and we set our area of interest, that is the full area defined in the input.netcdf file. We type Ctrl-Enter. The execution completes successfully. And we can now focus on the plot of the variables. So, first of all, we select the longitude of interest, that is 170, and we extract this level of longitude from the original dataset. We configure the plot. As usual, we configure the style of the title, the style of the label for the axis. And even in this case, we can type Ctrl-Enter to run this configuration and to plot our chart. So here in this off-model diagram, you can see the time on the x-axis and the latitude on the y-axis. The figure shows the seasonal cycle of the chlorophyll at the boundary between subtropical and subpolar gyres of the Pacific Ocean. We see a very oligotrophic region with very low chlorophyll levels all year long south of 28 degrees north. Further north we see a marked seasonal cycle typical of subpolar gyres. A spring bloom due to the mixed layer restratification, followed by a period with very low chlorophyll levels, very shallow mixed layer in summer, and the deepening of the mixed layer in autumn, associated with increasing chlorophyll concentration. So we are now at the end of our notebook, and I would like to thank you for the attention, and I hope you enjoyed the global biogeochemical training and the data provided by Copernicus Marine Services. Thank you.